Good morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. Today, we are going to start a variable speed drive or variable frequency drive for irrigation pumping. So, pumping water for irrigation can be a major expense for irrigation farm. In 2003, more than 5 lakh pumps were used for irrigation and the total estimated energy cost nationwide was over $15.5 billion. Improving the efficiency of irrigation pump has many benefits, including improving and profitability of the irrigated farm. When a single pump is required to operate over a range of the flow rates and pressure, a standard procedure is to design the pump to meet the greatest output demand of both the flow and pressure. For this reason, the pumps are often oversized and then will be operating inefficiently over a range of duties. This common situation presents an opportunity to reduce the energy requirement by using control methods such as a variable speed drive. Most existing systems requiring a control method use bypass line, throttling valves, multiple pumps, or the pump speed adjustment. The next figure through 3 illustrate the common control method, including the variable speed and the potential energy saving, and often changing the pump speed is the most efficient method of control. And when a pump speed is reduced, less energy is used by the pump's power unit and therefore less energy needs to be dissipated or bypassed. See this diagram, it is a bypass control and it is a throttle control. So how much amount of the energy can be lost by using the bypass control and how much energy is wasted during the throttle control. Pump speed refers to the rotational speed of the pump shaft and the shaft is connected to the impeller. This impeller adds the energy to the water. Slowing the rotation of the impeller reduces the energy that is transferred to the water and thereby the power requirement of the pump. The pump speed can be controlled in a number of ways as a mechanical drive lines directly connected to a variable speed engine, then by using hydraulic coupling, again by variable speed pulley arrangement, changeable gearbox that is constant speed input with variable speed output, and magnetic coupling that is constant speed input with variable speed output, and last one is the electrical induction motor using a variable frequency drive. Let us see the pumping system by using the hydraulic characteristics. The pump can be placed into several broad categories, including a positive displacement and rotodynamic. Most pumps used for agriculture irrigation pumping are rotodynamic, and it's meaning that they transfer the energy to the water by means of a rotating impeller. Pump add the energy to the water by raising the height of the water and increasing the pressure of the water as it exits the pump. This pressure is used to move the water through the irrigation system and overcome losses. When evaluating the pump, a system approach should be used that includes all components: energy input via pump and pressurization requirement of the irrigation system and energy to overcome the friction losses in the system. The total energy requirement for a pumping system is defined by the static head and the friction head requirement of the system. In pumping system, the total energy is often referred to as the total dynamic head. This total dynamic head has two components, that is static head and friction head. Static head is the sum of the difference in elevation of the supply and delivery point of a liquid being moved plus pressure head. The static head is independent of the flow rate and it is shown in the next figure. This friction head is the energy required to overcome the friction losses in the system caused by a water being moved in the through pipe, wall, and other components in the system. This loss is proportional to the square of the flow rate. And the third component of the total dynamic head is the velocity head. This component is generally small in irrigation system and is often ignored because it is normally significant in comparison to the static and friction head components. In order to select a proper form, the system operating characteristics need to be unknown and a system curve relating the flow rate to the total head needs to be developed. In general, the system curve will consist of the sum of the static and friction head as shown in this figure. The performance of a pump is typically shown graphically in a pump curve, and a pump curve shows the relationship between total dynamic head and flow rate. Rotodynamic pump have curve where the head falls gradually with increasing the flow as shown. When the pump curve and the system curve are combined, the intersection of this pump and system curve is at the point where the pump will try to operate. A demonstration by the affinity loss is shown, and change in the pump speed greatly affects the power requirement. A slight reduction in the speed can result in significant reduction in the power in the input power. The potential energy saved varies depending upon the type of the irrigation system supplied and pump selected. When the pumping head required by the system is mainly a friction loss, reducing the speed causes the pump operating point on the system curve to follow the path of the efficiency curve and allows the system to operate over a range of a speed at or near the base efficiency point, that is BEP of the pump. The reduction in the flow varies proportionally to the speed, and the affinity law accurately predicts the flow rates and head change as well as the power saving. When the majority of the pumping head required by the system is due to the static head of the work of the pump is used to lift the water to a certain elevation. Changing the speed of the pump will cause the system curve to cross through the more efficiency. The reduction in the flow varies proportional to the speed, and the affinity law accurately predicts the flow rate and head changes as well as the power saving. When the majority of the pump head required by a system is due to static head, that is when most of the work of the pump is used to lift the water to a certain elevation. By changing the speed of the pump will cause the system curve to cross through more efficiency lines and not follow the best efficiency point. The flow reduction is no longer directly proportional to the speed changes, and not only are the energy saving not as the great, but they are more problematic to calculate because of the difficulties in determining the change in the pump efficiency. The shape of the pump curve also has an effect on the potential energy saved. The pumps with the steeper curve have more potential to save more energy. Thank you.